Welcome to qnawire.
So we're doing chapter 18, problem 61. It says the second postulate of kinetic theory is that molecules are on the average far apart from one each other. That is, their average separation is much greater than the diameter of each molecule. Is this assumption reasonable? So to check, calculate the average distance between molecules of a gas at STP, standard temperature and pressure, and compare it to the diameter of a typical gas molecule, which is about 0.3 nanometers. And if the molecules were the diameter of ping-pong balls, roughly 4 centimeters, how far away would the next ping-pong ball be on average? Okay. So we want to calculate the volume per molecule from the ideal gas law first, and assume the molecular volume is spherical. So to do this, we can rewrite the ideal gas law in terms of the volume per molecule. And this is kBT over P. And we set this equal to the volume of a sphere. So now we can rearrange to solve for R of the volume is 3 kBT over 4 pi times the pressure to the 1/3 power. And cool. So this is the intermolecular radius. So the intermolecular distance is 2 times this, so 2 RV. So 2 times the cube root of kBT, 3 kBT over 4 pi p. So this is the distance between the molecules that we want to find. So let's go ahead and plug that in for our first case. So this is 2 times 1.38 times 10 to the negative 23 times 273 Kelvin all over 4 pi times 1.01 times 10 to the 5 pascals. And this comes out to being 4 times 10 to the negative 9 meters. So this comes out to being roughly 130 times the molecular diameter, because we can do d volume over d molecule, and that is 4 times 10 to the negative 9 over roughly 3 times 10 to the negative 10 for the air molecules. So this is 13.3. So that means if we say the d molecule is roughly 4 centimeters, then the intermolecular distance is roughly 13.3 times that. So 13.3 times d molecule is roughly 50 centimeters. Cool. So yeah, what it's saying is we have the intermolecular distance in our volume is roughly 13 times that of the molecular diameter.